Today we're going to be drawing Lewis dot diagrams for covalent compounds, both polar, nonpolar, and eventually we'll get to some exceptions which are called coordinate covalent bonds, and we'll draw those as well. So let's start with the nonpolar and we will work our way up. So for nonpolar, the first thing you have to do is you have to look up the configurations on the periodic table. Hydrogen's configuration is just one. So when I draw hydrogen bonding to itself, I just draw two H's. They each have one valence electron. It doesn't matter if you put them at the top or if you put them on the inside. And since it's covalent, we circle it. When we draw our Lewis dot, the circled electrons become a line, the formula, H2, and the name for the shape, linear diatomic. Diatomic meaning it's two atoms, linear means it's a straight line. F2 is going to look like this. They are 2, 7, so I'm going to put 7 dots on these. Now I know I'm going to circle one pair, so what I'll do is I'm going to put the second set in reverse. If you didn't, it's not the worst thing in the world, and then I can make a nice even circle in the middle. If you didn't, then you'd have a long circle, but it's fine. The two electrons that get circled become the bond. And then the three pairs around it get written in, don't forget them. And we have some special names we have to mention. The pair of electrons in the bond are called the bonding pair, or the bonding electrons. And this would be for a single bond. Okay. And then a pair of electrons that is not bonding, these would be called a lone pair, and there's 3 lone pairs around each one. So they're lone pairs, and then we have bonding pairs. That's just terminology. So any pair that's not in a bond is called a lone pair. Any pair that is in a bond is called a bonding pair. And if only one pair is sharing, we call it a single bond. I'm calling it a single. Obviously, that means we're going to go up from there, but we'll get to that later. Formula F2, name of shape. Still linear diatomic because it's 2 atoms and it's a straight line. Next one, oxygen is 2,6. So when 2 oxygens bond, in order to become stable, they're going to have to bond twice. So I'm going to circle the single electrons, and the lone pairs never bond. And there we go. Now when I clean this up, I'm going to put the 2 electrons that I circled right in the middle. Okay, I know they don't look like they're in the middle here, but when we're done, they will be. And then for these lone pairs, it doesn't really matter. Technically, if you put the second pair, I'm going to put the second pair underneath just to keep them symmetrical, but that's not really right. And if you left them where they are, it's also not really right, but either is fine. The truth is kind of a little more complicated, so we're not going to get into that. But this way is fine, or leaving them here is fine. None of that matters. And this is called a double bond. Formula O2. And it's also linear diatomic. Nitrogen is 2, 5. You hopefully see the pattern at this point. So I'm shifting the way I put my Lewis dots on them. I still go one and then around and around, but I just started at a different spot because I already know what's going to happen. These are going to have to bond together 3 times. And again, this is just the octet rule at work. Nitrogens are 2, 5. They want to become 2, 8. They need to make 3 bonds to do that, so they're going to have to bond to themselves 3 times. When I clean it up and draw my Lewis dot diagram, my actual formula, or my model, it's going to look like this. 3 bonds, the 3 lines go right into the middle. The lone pairs, you could leave them exactly here and here, but in theory, you could have put them up, down, side. Doesn't really make a difference to me. It's not really going to matter. Formula N2. Still linear diatomic. This is called a triple bond. Now, just be aware, because if you notice, if you're just given the formula, they expect you to know what's going on, that to understand that there's a difference between F2, O2, and N2 based off of the valence electron number and the octet rule and how they bond to become stable. So if you look at them right here, if you just look at the formula, they all look like basically the exact same thing. But then if you look at the bonding and the Lewis dot, there's a lot going on, and they are not 100% identical. So just be aware of that. In chemistry, a lot of things are, it's really left for you to understand. Next page. Now we'll get away from the non-polar covalent and we'll get to polar covalent. So the thing about polar is, remember, with polar covalent, you're going to have an arrow that points towards the negative from the positive, and it's based off of electronegativity. The negative is the higher electronegativity. So H is configuration 1, F27. So when I draw it out, they both need to gain 1, so I make one circle. The circled electrons go right in the middle. Again, if you put this dot here because you knew what was going to happen ahead of time, and then you just made a nice cleaner circle in the middle, that's fine. I did it this way just to show you that if you make a mistake, that's totally fine too. And my arrow points towards F because F is the negative end, because it has higher electronegativity. You would have to look that up if you didn't know that. Formula. It's just HF, name of shape. Still linear diatomic because it's still 2 atoms, and that has nothing to do with which atoms they are, and therefore they form a straight line. The rest of them will start not seeing straight lines anymore, for the most part. Next one, H is 1, O is 2, 6. So even just looking at this, we can say, all right, oxygen needs to gain 2 in order to be stable. Hydrogen only needs to gain 1 in order to become stable. So you're going to need more than 1 hydrogen to make an O stable. So I'm going to draw O first. And the reason I draw that is because O needs more bonds, so I'm going to put that one in first. And I can see, and again, this is where it gets a little bit more complicated, you can see that there's 2 singles, and they're here and here, right? And so I'm going to have to make 2 bonds, one here and one here. So 1H is going to bond to that, and 1H will go down here and bond to that. Now, if you do it this way, which is the way you're supposed to, look at that shape. It's starting to actually tell you the shape. When I draw it out exactly as I see it. So it looks like this. And then my polarity arrows, I need 2 of them, 1 for each bond. Meaning this is now my negative end of the molecule. You can see that because they're pointing in the same direction. And this end's my positive end of the molecule. Now, if we look at the formula, H2O, because there's 2 H's, the positive thing tends to go first, or in this case, the partially positive thing goes first, right? And name of shape, bent triatomic. You could also call it V-shaped. That's fine too, but you can see there's a clear bend. And I'll show you what happens. There's a way to tell. There's 2 scenarios where you have 3 atoms, and they can either be bent or they can be linear. And I'll show you how to tell the difference when we get to the next one that happens to do that. The next one, 1 and then 2-5, so you can already figure it out. Nitrogen is 5. It's going to need to make 3 to become stable. Hydrogen can only make 1, so I'm going to need 3 hydrogen for one N. You get the idea. N goes first. I'm going to put 1 hydrogen over here, 1 hydrogen down here, 1 hydrogen over here. When I draw my Lewis dot, it's going to look like this. Don't forget about the lone pair. My polarity arrows all point towards nitrogen because it has higher electronegativity. My formula, you would technically write H3N, and that would be 100% right. I don't know why, but it's always typically written NH3. I think it's because it was done that way forever, and so they haven't changed it. But if you wrote H3N, you'd be 100% right too. So that's fine. So I'm going to write it as NH3, just force of habit. And the name of shape. Now, a lot of people sometimes would call this T-shaped. There is a more advanced theory that predicts the shapes of molecules, and it turns out when you build the model for this guy in 3 dimensions, it's not really T-shaped. There are T-shaped molecules. They are much more complicated. But if you actually draw this out in 3 dimensions, it actually kind of looks like this, where the hydrogen get pushed down a little and the nitrogen sits on top, and it's called pyramidal, because it kind of looks like a pyramid in 3 dimensions, although it's very hard to see in 2 dimensions. Next one. Carbon is 2, 4, hydrogen again 1. So carbon's going to have to make 4 bonds, so it's going to need to bond with 4 hydrogen to be stable. We're still using the octet rule when we do these. Okay, and when I draw it up, polarity arrows are all going to point towards carbon because it has higher electronegativity. Now, if you notice, it doesn't really matter if you draw the polarity arrow above the bond or below the bond. I'm just doing it, spacing them out so that they're not as cramped. The name of this, again, you have to really see the model for this. It kind of looks like this. It has the kind of downward part, like the pyramid, but then it has another one that goes straight up, and it's called, well, the formula would be CH4. Again, H4C is totally fine. Technically, it's actually right, but no one ever writes it that way. And it would look like this, and that's called tetrahedral. There's the name of that shape. Last one, and this is going to be the next one where I show you the alternative to 3 atoms. So there's 2 3-atom options. You have 3 atoms like H2O where you get a bend, and therefore the name is bent. And then you have 3 atoms like this one where it's not going to be bent, and I'm going to show you how to do it. So carbon is 2, 4, oxygen is 2, 6. Carbon needs to make 4 bonds. Oxygen only needs 2. So if I start with my carbon in the middle, I'm going to bond 1 oxygen to it. Again, I'm going to flip the configuration order because I know the answer already. So I'm going to bond once here and once here. So now this oxygen has gotten to 8. It satisfied its octet rule. It's done. It's not bonding anymore. The carbon, however, needs 2 more. Well, that's where another oxygen comes in. So it finds another oxygen, and then it can bond 2 more times with the other oxygen, and now you get this molecule. When I draw it out, it's going to look like this. Now again, I'm going to do this intentionally. So if you notice, I put 2 here on the side, and I did top side, I did top bottom. It doesn't matter. You could do them both like this. You could do them both like this. As long as there's 2 pairs, it doesn't make a difference. All right, and the polarity arrows actually point towards oxygen because oxygen is more electronegative. And now the name of this shape, this is CO2, and it is linear triatomic. And what I want you to notice is if you have single atoms, you get a bend. If you have, or I should say single bonds, and if you have double bonds, you get linear. That's the real difference. So if you have 3 atoms and they're connected with single bonds, it's going to be bent. If you have 3 atoms and they're connected with double bonds, it's going to be linear. The double bonds, the best way to think of it at this level is to say that the double bonds pull the molecule straight. They force the molecule into a straight position. Now, when we're eventually going to do a lab with this where you're going to do all this, but then you're going to take the extra step of building the model. So you're going to actually take a wooden model kit, and you're going to build these molecules using each, they're color coded for the different elements, and you're going to build them out and then draw them, and you'll actually see when you put that second bond in on that CO2, it does in fact pull the molecule back to a linear shape. There is a more advanced theory for this called VSEPR, which is valence shell electron repulsion modeling, which I may include a video of just for people who are really interested in why this is happening, but it's not necessary because there's just a few shapes that we have to really worry about. So that is the polar covalence. Now we do have a little bit more. we have our coordinate covalents, which I'm going to save for the end. And the next thing we're going to do are these. So I'm not worried about the shapes on these. We're just going to draw the bonding for these guys. The shape is not going to be as important because when the shapes get bigger, we stop naming the shapes. After the molecules get larger than CH4, we almost never, with very few exceptions, almost never name the shapes. So for these, what I want to show you is how these bonds work. So for this one, we've done this before. It's carbon, and it's going to bond to 4 hydrogen. And with these, I'm not even making you figure it out because that's not really what this is about. I'm telling you what's happening. And the Lewis dot's going to look like this. And then the polarity arrows go in. And again, as you get more advanced, a lot of times you'll see the polarity arrows don't get drawn because it's assumed that people understand that. So it just kind of makes the model a little bit too, there's a little bit too much on the model to, focus on. And so a lot of times you'll see them get dropped. You're not at that level yet where you get to drop them. Look at the next one. So the next one is CH3 with a Cl. So a lot of students have trouble drawing this one. So I'm going to start by just drawing what I know. I know it has 3 H's. So I'm going to put my 3 H's in. Okay, and now if you think about Cl, Cl is 2, 7. So Cl, based on the octet rule, only wants to make 1 bond. Well, that's very similar to hydrogen. Hydrogen happens to just have a configuration of 1, and because it's an exception, it also wants to make 1 bond. So a chlorine can effectively take the place of a hydrogen. So you can actually just do this. And so I lost an H, but I gained a Cl in its place. Now, I put mine at the top. If you put yours on the side or on the bottom, it wouldn't make a difference. And then, when we clean it up and draw it, it's going to look like this. Don't forget about the lone pairs. And last but not least, polarity arrows. For H and C, they go towards C, because C has higher electronegativity. For C and Cl, they go towards Cl, because Cl has higher electronegativity. So you do have to look at all of them. The next one, C2H2. So now I'm going to keep 2 H's, and then I'm going to substitute 2 Cl's. Now, be aware on this. Technically, you can write them. What I want you to do is whenever you have even amounts, I want you to oppose them. Like H here, H over here, Cl up, Cl down. Always oppose them. It's a little bit hard to show on the camera, but or in a video format, but when we build the model, I'll show you that in 3 dimensions, no matter where you put them, they will always be opposed in 3 dimensions. But in 2D, they can look like it's asymmetrical, whereas you want this molecule, if at all possible, to be symmetrical. And that will be our next topic, but we're not there yet. So when it's cleaned up, it's going to look like this. Next one, I'm going to keep 1 H now. Doesn't really matter which one you keep because this one can't be symmetrical no matter what. And polarity arrows almost all go out now. Oh, I drew a 2 on that one. Just get rid of this top one. Okay, so that's that. And then the last one, these are going to be all chlorines. So going to look just like CH4, except chlorines. Instead of H's. And then when we clean it up and draw the actual Lewis dot, okay, and then the last thing I need to mention, the arrows are all going to go out on this, and I see this a lot. This first column here is showing the bonding. This second column with the polarity arrows is the Lewis dot diagram. So don't confuse those. So if the test says give me the Lewis dot diagram and you show the bonding, while it may be very similar, it doesn't count as the same thing. The Lewis dot diagram is the cleaned up version where all of the bonded electrons have turned into lines and it has polarity arrows and things like that. This here is really showing me that you understand what's going on. The Lewis dot diagram is the final answer though, so be aware of that. And then the last thing I'm going to do, and then we're actually going to end this video because it is a little long, and then I'll put the coordinate covalent on a separate shorter video, is we're going to draw these three because we will eventually get here. So this is kind of like a little bit of a stretch or a reach, but you're definitely capable of doing this. So let's take a look. This is when you have two carbons. So the problem is, in order to have one, you need to draw this molecule. Whenever you see a chemical formula, what it's telling you is that all of these atoms are bonded together. It doesn't tell you how, but the one thing you can be sure of is that no part of these, there's no part of this that isn't connected to them in one giant molecule. Otherwise, it wouldn't be written in the formula. Like if some of these H's were like off bonded to themselves and not connected back to the main molecule, then they wouldn't be included in the formula because they would be a different molecule. The fact that they're all here in a formula tells me that they're all interconnected some way. So the first thing you always do whenever you have something like this with two carbons, start by bonding your carbons together. Now, if we think about this logically, we know carbons want to make 4 bonds. And we know that this carbon, if you do this, they can only make 1, 2, 3 more each. So 1, 2, 3, 4, 5, 6. Well, there happens to be 6 H's, so this should be pretty simple. So you draw them together like that. And when we draw our actual Lewis dot diagram, everything's gonna be in a line. Or all the circled electrons basically are in lines now. And there's no lone pairs because they're all bonded. Polarity arrows, they're all gonna point towards carbon. And if you notice, I didn't draw one for the middle bond. And the reason being is the middle bond is between 2 carbons, so the middle bond is technically nonpolar covalent, and the other 3 are polar. Now, there's more going on, which we will eventually learn, but for right now, that's totally fine. And so that's C2H6. Let's look at the next one. So it's done the same way. We start by bonding them together. We know that there should be 6 more bonds for each carbon, well, 3 more bonds each to be stable, but we only have 4 hydrogen. So what I'm going to do is I'm going to give 2 to 1, and 2 to the other. And then I'm 1 bond short. And notice it happens to be down here. So what I'm going to do is bond them together a second time. So now when I draw this out, it's going to look like this. Double bond between those 2 carbons. Now I'm going to draw my H's up and down. But if you drew them top side, wouldn't make a difference. And it's going to look like that. Polarity arrows for the bonds that are polar. No polarity arrows for the bonds that are not polar. Done. And you should be able to figure it out. Now, if you look, 6 H's, so I had 6 single bonds. I lost 2 H's, I gained an extra bond as a result. I lost 2 more H's, so you should see the pattern. You're going to get, so with this one, I just almost made the mistake that I was going to tell you not to make. If I put my H's top and bottom, I can still make these bonds, but I'm gonna have to like do some weird U-shaped circling, right? So what I'm gonna do just to make my life easy, I'm gonna bond one to the outside and the other to the outside so that I have room to make these clean. Now in the beginning, that may not be the case, and you may have to like, circle this electron with that electron and have these weird U-shaped circles, but when you do the Lewis dot diagram, it should look clean. Now if I put these up, fine, I'm gonna keep them all aligned. I like my molecules to be symmetrical, and you'll see why later on. Well, in real life, they are symmetrical, and if you learn the more advanced theory, you'll understand why, but we're just gonna say that they're pretty much always symmetrical when possible. So that is a little bit more advanced version of this. It's basically taking this concept of the CH4 series and expanding it to now 2 carbons. And again, it could go to 3 carbons, 4 carbons, 5 carbons. And that's actually a whole nother branch of chemistry that focuses on that. But for now, that's good. In the next video, I'm gonna break them up just because this video is long. I'm gonna do the coordinate covalent compounds. In this video, we're going to do the coordinate covalent compounds and the ion exceptions. So the 3 coordinate covalents that we need to know. And then there's some ion exceptions that are also, they're pretty easy. So let's start. So when you have an ion in a molecule, what it's really saying is this -1 here, it could be a positive, but the -1 is saying that you have an extra electron. Just like if an atom had a -1 charge, it means there's an extra electron. So basically what you do, and this happens a lot, is you're going to bond it up, and then you're going to be 1 bond short. That's where the extra electron comes in. Look at the most simple example. So when I bond O to H, and again, this is saying you have 1 O and 1 H, not as many as you need to make it stable. You just get 1 of each. And so when I bond this, I know oxygen has 6 valence, hydrogen has 1. I bond it. Oxygen's not stable. It needs 1 extra bond, but it doesn't have an extra atom. That's where the negative sign comes in. It means you have an extra electron to put where you need. I used a red X. And so when I do my Lewis dot, it looks like this. The name for this shape, still linear diatomic. Now, when does this happen? Why does this happen? This happens when chemical bonds form and there's a limited amount of extra atoms, or there's not enough. Normally, when H and O come together, they typically make water, but in order to do that, you need 2 hydrogen. Well, what if you had H and O together, but there literally wasn't twice as much H as hydrogen? They were just in a 1-to-1 ratio. Well, they'd end up forming something like this if they could at least grab an extra electron. So these are specialty circumstances. They don't happen very often. Well, frequently, but not not all too common, but frequent enough for us to talk about it. And so that's why we're mentioning it. So CN, same thing. Carbon normally 4 valence. Nitrogen has 5. Carbon will normally want to make 4 bonds. Nitrogen can only make 3 because once nitrogen gets to 3, it's stable, it stops. So carbon would normally need an extra bond. It would usually bond to like an H or some other molecule, but in this case there is no other molecule. That's where the negative sign comes in. There's the extra electron, it goes there. So it's basically like carbon had 5 valence instead of 4, and then it only needed to make 3 bonds. It's pretty much adjusting it. Name of shape. Linear diatomic. Now, coordinate covalents are a little different. They don't have charges. Well, they don't have negative charges. So what ends up happening with a coordinate covalent is this. So you start out with the base molecule, which is going to look like this guy, which is going to be NH4. So I'm just going to draw out the final version because we're going to save some time. No, I'll do the whole thing. So there's my molecule. And then you have an H plus. Now, in order to be a molecule, the fact that they're all in one chemical formula is saying not this. In other words, this H can't be separate from the rest of it. So here's what happened. Hydrogen lost its electron somehow. Some atom was strong enough to rip it away, or something happened where it lost an electron. So now you have a random hydrogen floating around, and it doesn't even have a single electron. It is very unstable. It does not want to be this way. It wants two, but it doesn't have any. So here's what it does. It says, wow, there's a lone pair here that nobody's using. Now, granted, nitrogen's using it, but not to make bonds. So it's just this lone pair just hanging out. Well, what does the hydrogen do? It basically jumps onto the back of the nitrogen and forces a bond to form. So the way we show that, we can't show it the same way as a regular covalent bond, because then we wouldn't know that there's something different about it. So what we do is you draw the bond as an arrow like that. I'm not going to put in polarity arrows, it would be too much. But it would look like that, and I just made it red. It doesn't have to be. So you just use an arrow like that to show that this bond is a coordinate covalent bond. So it's covalent, but it's not a normal style of bonds. It's basically both, one atom is supplying both electrons to the bond, which does not normally happen. And so this is a very unstable bond, but basically having hydrogen be separate is worse than having hydrogen be attached to the back of nitrogen where it shouldn't be. Okay, and so this is still a better scenario than this, but if anything else comes along where this hydrogen can get a better deal, like its own electrons, that it doesn't have to borrow two from somebody else, this hydrogen will pop off and go that way. And so that makes these molecules very unstable, but they are very useful for us. This is ammonia. It's used in cleaning supplies. It's why when you clean, when you clean your bathroom using stuff that has this, you're supposed to leave the windows open. It really kind of burns your nose when it stings. It's not good to breathe in for that exact reason. It's this hydrogen that makes it a great cleaner, because it can jump off and attack bacteria and viruses and take electrons right out of their cell wall and things like that. But it's also what makes it not great to breathe in. Name of shape. When it's like this, it's tetrahedral. Next one, oxygen can do this too. So we have the exact same scenario happening. Oxygen has two lone pairs. We have a hydrogen without any electrons coming along. It really wants some electrons, so it jumps onto the back of the oxygen and it forms H3O, which looks like this. Now, a lot of times you will see them not drawn this way. They'll just make it a regular bond, because chemistry tends to be a little elitist, and they say, oh, well, anyone who sees H3O with an oxygen with 3 bonds automatically knows this is going on, so I don't really have to draw it out like this. You do. You're not that advanced yet. But that's pretty much the way it works. And again, same thing. This H will pop off. Any chance it gets to, the moment it gets a better deal, it'll jump off and take that deal. But it's still, this scenario is still better than regular random H with no electrons. Name of shape. Pyramidal. And then the last one, this one's a little different. It's not done the same. It's carbon and oxygen. So carbon makes 2 bonds. But now carbon needs to make 2 more. So normally it would find another oxygen, but there isn't another oxygen. So what does it do? Well, it's super unstable, but in this case, oxygen can actually donate both electrons to the bond. And so you end up with that, which is called carbon monoxide, not carbon dioxide. And this actually is a pretty important molecule, because every year people die from carbon monoxide poisoning, because what happens is when the temperature goes down, obviously it gets cold at night, and this time of year, the heat kicks on at night, and what will happen is people's furnaces will have soot build up, and that soot will build up and restrict the oxygen flow into the furnace, right? And when that happens, you now have carbon-based fuel being burned with not enough oxygen, and instead of making CO2, which would normally be the byproduct of CNO, since there's not enough oxygen to make CO2, you get just CO, which is carbon monoxide. And if that soot backup, that the backup that's the same backup that's preventing the oxygen from coming into the house is also preventing the CO from leaving. And then the CO backs up into the house, and that's how people die, because it fills the house with carbon monoxide, which we can't breathe. We physically can breathe it in, but it doesn't do the same thing as oxygen for our lungs. It doesn't provide our cells the oxygen needed for them to survive, and you end up dying from this. And one of the worst parts about it is one of the symptoms of carbon monoxide poisoning is being tired, and this typically happens in people's houses in the evening when everyone's sleeping, when the temperature drops, because that's when the heat kicks on the most often. And so it does happen every year, and it's part of the reason why you have to keep a carbon monoxide, or you should have a carbon monoxide detector in your house, because in the winter particularly, this is when you're most susceptible to this. Name of shape. All right, and these are all the exceptions that we're going to deal with bonding, and that's it. It's literally going to be these three. There are no other versions, and it's going to be these two ions, and you're never going to have to deal with another ion or another polyatomic. Now, in terms of regular covalent bonding, yes, we can expand that, and we're going to do a lot more with that. But as far as exceptions, this is the 100% list of exceptions. There will be no more exceptions for bonding other than the ones I mentioned.